All right. Are you guys good? I'll just wait for this. All right. All right. Hey, everyone. Thanks for coming, and welcome to our talk. So today, me, Remy, and my partner Kevin, we're going to talk about how to use Vulkan for mobile VR. Specifically, where the goal of the talk is not really to get you guys started in writing a full Vulkan application from scratch, because that's completely undoable in the mere 45 minutes that we have. But we've been working on Vulkan a lot at Oculus this year, and we noticed that there are some things that aren't super well explained online because they're pretty custom to VR. Things such as multiview, foveated rendering. And so we really wanted to talk about those today, because although there's a lot of resources online, the VR-specific things we think we can help with. So first, let's just explain quick things about Vulkan to start with. What is Vulkan? So Vulkan is an API designed by Khronos, and Khronos is a consortium of companies that work together to create open standards, such as OpenGL, OpenXR, and very obviously Vulkan. And what Vulkan does is that it's a CPU API to control the GPU. So although there is a shared language, although it's not even really a Vulkan shared language, it's called SPIR-V, it's the same as the one from OpenGL, most of the Vulkan code that you're going to be writing is going to be executed on a CPU, not a GPU. And this is pretty important because a lot of times I hear people tell me, well, obviously since you moved all your code to Vulkan, your GPU is running faster, right? But if you think about it, if you're telling the GPU to do the same thing, whether you're telling it to do the same thing on Vulkan or on GL, the GPU is going to go the exact same speed if you're doing your job right, and it's the CPU that's going to go faster. So this is pretty important to understand, that Vulkan is really a CPU API. And what it does is it controls the GPU. So obviously it's not the first time anybody created an API to control the GPU. And before, what we had was OpenGL and OpenGL ES. So OpenGL and OpenGL ES have been pretty weird for a while, because OpenGL ES, they've been on like a ping pong schedule, where OpenGL ES has always been on like a 2 to 3 year delay compared to OpenGL. So if you think about most OpenGL versus OpenGL ES code, most of the things you're writing are actually completely cross-platform, so they run both on mobile and on PC. But then you always have that one function that's like GL buffer subdata, which works on GL, but it's still an extension on GL ES, so now you need to add an ext with an if Android on it. So it's been weird for a while. And this is where Vulkan, one of the Vulkan founding principles really, is to be cross-platform. Vulkan is both a PC and a mobile API, so the exact same code should run the same way. It's not going to run at the same speed, obviously, it's not magic, but it should do the same thing. And for us at Oculus, it's very, very important, given the fact that we are a company that has both very deep mobile interests with Quest, but we also have a PC API, and we're trying to align them. So this is one of the reasons why we were interested in Vulkan. If we talk quickly about the advantages of Vulkan, the first one is that it has a it has a very significant lower CPU driver overhead. And this is for plenty of reasons, but one of them is that it literally does less things for you. Vulkan inherently is a significantly lower level API than GL. And so while GL kind of interprets a lot of the things that you asked it to do, Vulkan, you need to write more stuff in Vulkan to do the same thing as GL, because you're way more explicit. So the driver itself needs to do less things. Another interesting way that it has a lower CPU driver overhead is because in release mode, when you remove all the validation layers, Vulkan does pretty much no error checking. If you give it a pointer, it's going to deserialize it. It's not going to look if the pointer is null. And that is because it has a really, really good layer system that if you want to have debugging going on, you attach the layer on top of your Vulkan runtime, and then you have plenty of debugging. But when you ship the application, you completely remove that, which lowers the cost in terms of time of running those functions. Another thing that's really core for us is that it does cross-platform standardization of extensions. So there are extensions such as Multiview, for example, that were mobile only for a while. So on mobile, it's like GL OVR Multiview 2, that you could never run on PC. So when you were doing PC development for Quest, then you could not run Multiview. So we had other PC ways to do the same thing, but it was kind of annoying. Whereas lots of extensions on Vulkan, such as the things that Kevin will talk about later, like foveated rendering, are core. Another thing that is really, in my opinion, important when you look at API design is that it switches from stateful to stateless. So OpenGL is a stateful API. When a function executes, it executes within the state that the GL driver is in at that point. So if you just look at a function that does, let's say, GL bind buffer or GL bind texture, it's actually only valid within the context of all the other functions that you executed before, because that function will go modify a state, but you don't really know what that state is. Vulkan is completely stateless, so when you execute a function, the function has as argument everything it needs to execute with structures being nested that you give into your function. This causes way less issues and it's way more clear. And then on top of that, it enables us to do multi-threading, which is a core thing in Vulkan, that you can do multi-threading. Because since you can't do multi-threaded stateful, because then you would have multiple threads basically racing access to that one state, and then it would completely fail, which is why Vulkan went to stateless and enables multi-threading. And then the last thing, which will go in pretty detailed explanations of this, is that it's very explicit. There's a lot of things that the GL driver looks at how you're submitting your commands, and then it's like, since they're submitting those commands this way, I should probably do this in order to go faster. And most of the time it's right, but sometimes it's wrong, because you didn't provide it enough data, or you didn't understand that it was going to do that. And Vulkan completely removed this by asking you way more stuff, but then it's very explicit what you're doing, and a lot of bugs that we saw over and over again on GL ES applications just will not be done, because it's asking you exactly what you want. So, before we can really understand all of the concepts that I explained here, since it's lower level, I want to go back a bit to GPU architecture, specifically the differences between PC and mobile, because if we really want to go fast on the mobile render, you need to understand the core differences on the hardware on the chip in how it runs. So if we think back quickly about desktop GPUs, desktop GPUs are what we call immediate mode. And this is kind of an oversimplification of those concepts, but this is kind of how it actually works. The GPU executes commands as soon as they're available. So basically, as soon as you have a draw call and you flushed it, the GPU is like, all right, let's go. This is why here you have the CPU render thread on my little timeline show, and the GPU starts as soon as the CPU render thread starts actually sending commands. So this is nice because you have pretty low latency, and as soon as you have something available, the GPU starts on it. But if you think about the bandwidth, it actually inherently requires a lot of bandwidth to do that. If you have, let's say, 100 draw calls, that's not that much on PC, but if you have 100 draw calls, for each pixel of each of those draw calls, you're going to need at the very least, if you think about how rendering geometry works, you're going to need to do one sample of the depth buffer in order to figure out if your triangle is on top or below. If it's below, then effectively you just discard and you go to the next one, so you don't do anything. And then if it's on top, then you need to, at the very least, write the new color and write the new depth. So per useful pixel, you at least have one read and two store, so 3 bandwidth access. And then if you have translucency, you also need to read the previous color and a bunch of other stuff. But you understand that, and this is what those little white arrows are representing, is all those bandwidth access, read and write and read and write and read and write. So this is fine for desktop GPUs because you've got a 300 watt power plant on it. So this is all fine because bandwidth really is very power heavy. And you don't have that much heating issues because you've got 2 fans on your single GPU that like weigh as much as Quest. So that's cool. But you can't really do that on mobile. And so on mobile, the first thing you need to do is reduce your bandwidth. And this is where tiled renderers come on. So tiled renderers isn't like a concept that is specific to Quest at all. It's mobile. It's a mobile concept. But this is how the mobile GPU on Quest works. So on Quest, the GPU, the parallelism that we had before completely goes away. And the GPU executes frame buffer commands, so for commands to render into a texture or a frame buffer, when they're all submitted. So when you do 5 draw calls, the GPU does nothing. It's probably rendering the previous image, but even if it could, it would do exactly nothing. And then you have those 3 stages that I show here. The first one is binning. So now that you have all of the, I'm sorry, can you remove the light? Yeah, thank you. When you have, I'm sorry, yeah, so the first thing is binning. So you execute the vertex shader of all the draw calls, and you effectively figure out if you were to divide your screen in subtiles, so approximately 100 pixels by 100 pixel subregions, you just figure out per draw call which tiles that draw call hits. So if you render the sky, it's probably only going to touch the top tiles, and if you render like your hands at the bottom, it's only going to touch the bottom tiles. And then per tile, you do render and then store. So you're going to render all the draw calls for that tile, and you know that because you just did the bidding pass, and then when you're done rendering that tile, you store. So, and you do that because effectively we added a new hardware between the render cores and the system memory, which is the tile memory. So you have a very small, very, very fast cache that is right next to the GPU cores. For us on Quest, that cache is 1 megabyte. On 1 megabyte, I'll spare the calculations, but approximately you get 100 pixels by 100 pixels if you're rendering with a depth buffer with MSAA 4. So we're subdividing that screen in rectangles of 100 by 100 pixels, and then we're rendering them sequentially. So you're rendering the entire draw call count for the top left tile, and then when you're done doing that, you store the results of that tile, but only once, because now all the draw calls for that tile have been computed, so you only store the color value of that tile once to the system memory. So instead of doing loads and store and load and store, those loads and store are being done on that super small, super fast cache, and then when it's done, you only store once. You can even be smarter than this, and we'll get to this later, by thinking about the fact that, for example, your depth value, although it was obviously necessary when you were rendering all the draw calls in the tile, when you are done rendering the tile, you don't really need a depth buffer anymore, unless you're doing some sort of depth-based post-pass, which most people don't do. You can literally just discard it and leave it on the tile because you'll never need it again. So this is how we get significantly lower bandwidth. Although we get a GPU that is slower, but not that much slower in terms of like execution capabilities, the bandwidth goes way down compared to a PC GPU. And we really need to continue optimizing our apps and our graphics APIs to be able to configure the GPU in understanding that lower bandwidth. So this is where we're going to start understanding how Vulkan really does its things. So the first thing I wanted to talk about today is MSAA. So MSAA, I can't get into exactly what MSAA is, but for most people that know what MSAA is a quick way to decouple what we call visibility from shading, so that although you don't shade, so you don't calculate the fragment shaders, you don't calculate the expensive pixel cost of more pixels, you do rasterize them so you have many subsamples in terms of depth to really get significantly smoother edges instead of getting aliasing. And this is very important for VR because in VR, although we render into high resolutions, those high resolutions get warped into lots of degrees because you have the screen right here. And so you really need to get those edges like nicely smooth and not aliased. So if you think about how you do MSAA on PC, usually you have a two-pass system where your first pass you render into an MSAA texture that has those four, if you run MSAA 4, that has those 4 subsamples per pixel, and then you store them, obviously, and then you load them again into the GPU and you average them together to get a single nicer pixel that then you will use to display to the screen or do post-processing on. But if you were to do that on mobile, then again, you would have that storage and bandwidth problem where the first store that we talked about before would be a 4x store, and then you load it again and then do the averaging and then resolve the final pixel that you can use. So MSAA on mobile, although lots of people have issues with it when they start doing Quest development, MSAA on mobile doesn't really work that way because when you remember that this was the execution capabilities that we had before, MSAA on mobile actually adds another step between the tile 1 render and tile 1 store. So per tile, you actually add a resolve that is done on the hardware side. So although the rendering is being done with MSAA, before you store anything, you do the averaging on the tile cache so that the tile cache then has this final average pixel, and then you only store that one single sample. This is why, for example, on OpenGL, I have this question all the time by OpenGL Quest developers that are using RenderDoc to inspect their applications, and they tell me, yeah, like I thought I enabled MSAA in Unity and Unreal, but I'm RenderDocking my application and looking at my texture, and it's not an MSAA, so I did something wrong. Can you please help me? And actually, no, it's because the MSAA was done on the chip, but the final texture is not MSAA, so that the transfer between the tile cache and the memory only had that one pixel, which is effectively what you want. So this is how MSAA works on mobile. And that is why a lot of people say MSAA is free on mobile. It's not free, but it is significantly cheaper in terms of execution times than if you needed to do that two-pass thing. So as I said before, in Vulkan, everything is explicit. So although in GL, a lot of the details here were obfuscated by the GL driver, you effectively had an MSAA frame buffer and you attached a non-MSAA texture on it, and it magically worked. On Vulkan, you need to ask exactly what you want. So Vulkan applications are oriented around something, a structure called VK render pass create info, which is how you create your frame buffer renders. And this is where you're going to need to configure MSAA. This is what we did, for example, in Unreal Engine 4 when we tried to get MSAA on Vulkan working on Oculus Quest this year. So here you actually have two attachments. So attachments is how you attach basically textures to frame buffers. And instead of having one, you have two, as intended. You have the color attachment, which is going to be your 4x MSAA color. And then you have the resolve attachment, which is the attachment that only has one sample that you want to use afterwards. So this is how you attach them. And I'm attaching code here. It's not super important to get this code exactly right. I'm just trying to understand, to explain how Vulkan wants you to architecture things more than like it's image layout and not layout image. And then when you actually configure the attachment, this is where the fun happens. So first you need to configure the color attachment. So this is a BGR8 sRGB texture, nobody cares. And it has 4 bits per sample because the color attachment is actually the 4-bit one. And then we get into those load up and store up here, and this is extremely important. This is how you configure the bandwidth transfers between the tile memory and the system memory. So the load up, so the load up is how you load the contents of the tile memory. So if you think about it, there's kind of two ways that you can do this. Either you clear it, that means that you don't really care what was in the texture before, you're just going to clear it to your clear value. Or you load it. That means you take the results from the previous texture and you load the tile memory with this so that the new render can render on top of it. It is very important that you clear and do not load, because if you were to load, that means that when you start rendering, on top of this little render and then store thing, you actually have what we call an unresolved, which is a bandwidth transfer between the system memory that loads the previous content of the texture back into the tile cache. We have devs, for example, sometimes tell me, well, it's actually going to be faster. I'm going to save the cost of the clear by just knowing that I'm going to render on top of everything anyway, so that way I don't have to clear and it's going to be way faster. But actually, no, it's significantly slower if you do this, because the clear tells the GPU, instead of transferring all that memory from system memory to tile memory, you can just initialize it to like 1. So this is really important. And then the store here tells the driver what you want to do with those pixels afterwards. And then here I say don't care, because for the color 4x MSAA one, I do not want it to get out of the tile memory, because what I want to get out is this averaged one sample one, but the 4x MSAA one I'm specifically uninterested in after this. This is why right below I have this resolve attachment configuration thing. The format is the same. Samples is 1 bit because this is the average non-MSAA texture. Load is clear, same thing. And then this one I actually want to store. And so all of this tells the driver exactly what I want it to do. I want it to clear everything so that the tile memory does not incur any bandwidth transfer when I'm starting the rendering. And then I only want to store out the single sample MSAA averaged one, and especially not the 4x subsampled one that have a huge bandwidth cost. And this is how you configure MSAA on mobile in Vulkan. And if you were to download, for example, like Unreal Engine on Vulkan, this is exactly what you would see in RenderDoc if you were to inspect the render pass. The other thing I want to talk about Vulkan and how to optimize your applications is Multiview. So in Multiview is both OpenGL and Vulkan feature that allows us to use the fact that although the rendering is going to be different for the left eye and the right eye in VR applications because your eyes aren't in the same spot, so you need to have different view and projection matrices, most of the objects that you're going to see on the left eye, you're also going to see on the right eye, so you don't need to duplicate the draw calls. If you were to render an application kind of naively, a VR application naively, and this is what we used to do in the beginnings of VR rendering, it would look like this. If you had 3 objects in your scene, it would look like this. So you do left eye draw calls and then right eye draw calls. So this is 6 draw calls, and more than 6 draw calls, it's actually usually on the engine side 2 scene traversals, which depending on your engine can be pretty expensive. But if you think about it, all those objects, obviously on this beautiful little image, are the same. So you can actually configure your render pass and your graphics card in order to not need to duplicate the draw calls. And then it would actually look like this, which makes sense. So we did this on GL using GL OVR Multiview, and I just want to talk quickly about the Vulkan way to do things. So on Vulkan, as I said before, this got cross-platformed. So there's an extension called VK or Multiview that allows you to do exactly that. And the cool thing is that it actually got promoted to Vulkan 1.1 core. So that means that every graphics card and driver that says that they're 1.1 compliant will need to do this. That means, and since most PC graphics cards are 1.1 core, that means that you can run this code on PC and on mobile, because on Quest it supports this. That makes it way easier to do porting from one platform to the other. I've seen, I just want to talk quickly about the fact that, Multiview, although usually if you did non-Multiview, you would have two textures, one for the left eye and one for the right eye, or UE4 does double wide, so a single texture with both inside. The one way to do Multiview is to render into a texture array. And by design, how it works is that slice 0 is the left eye and slice 1 is the right eye. I have seen people actually allocate their own texture to the array on their end and then render to that on their engine and then copy the results, slice 0 into the left texture and slice 1 to the right texture, which incurs, again, another copy and a bandwidth transfer. It's important for you guys to know that on the VR driver side, we actually have an enum when you allocate a texture that says specifically, I would like this texture to be a texture to the array, specifically so that you can render directly into the swap chain that you need to render in Multiview. And how you configure this is by using the PNX style Vulkan extension model on, again, VK render pass create info, so the same thing as MSAA. And it's pretty easy to use. You need to give the number of subpasses. Subpasses is a Vulkan concept that Kevin will talk about later. You need to give it the number of subpasses you want Multiview to be enabled on. And then you have this view mask system, which effectively asks you to give the driver the number of views you want enabled in Multiview. So for us, most of the time, we want the left eye and the right eye, so that's 2 views. So you need to enable view ID 0 and view ID 1. And so if you have if you have this huge 0-bit string and you just want to enable bit 0 and bit 1, that's 0x11, which is 3. And so you just put in the pview masks as that I have here, you put 3 and 3, and that just works out of the box. If you wanted Multiview 3 because you wanted to do like a center eye or something, you'd put 1, 1, 1, and so that'd be 7. And that's pretty much it for Vulkan Multiview. But it's really important that everybody uses this because it does get your number of draw calls way down. And now that I explained MSAA and Multiview, I will give it to Kevin so that he can talk about foveated rendering. Thanks. Thank you.
Thank you, Remy. So, after MSAA solves your aliasing issues and Multiview cuts down your CPU costs, well, congrats, you're now GPU bottlenecked. Luckily, Vulkan has something for that too, with a revamped implementation of fixed foveated rendering, which has been an important part of improving GPU performance in mobile VR. Now, before we dive deeper into the new Vulkan APIs, let's take a quick look at how it started in OpenGL ES. So the GLES implementation used the Qualcomm texture foveated extension, which is enabled on a per texture basis through the texture parameters that you see here. It uses a predefined set of parameters that are applied to a fixed falloff rate in the driver, which controls the resolution that each tile will render at. For an Oculus developer, these parameters are defined by the Oculus runtime based on the foveation level that you set in your application, and are applied to the iBuffer textures automatically. So really, you don't really have to write any of this code here. Now, this approach allowed us to add FFR without any underlying changes to the rendering pipeline on the application side. So while the GLES implementation provided a basic but effective entry point into fixed foveated rendering on Vulkan, we wanted a bit more. And so enter Vulkan's fragment density map. Now, just with the fragment density map extension name alone, there are 2 noteworthy points that I should acknowledge first. The first is that while the GLES extension was prefixed with QCOM, this one drops that for the generic EXT prefix. This indicates that the extension is not Qualcomm exclusive and will enable more cross-platform compatibility in the future. Second is that this extension doesn't mention foveation anywhere. Well, this is due to the fact that the extension isn't necessarily restricted to foveation at all. In fact, if you've been following developments in other graphics APIs, you'll see a lot of similarities between this and variable rate shading in DirectX 12. The general idea here is that this extension enables a new type of attachment on the frame buffer level, which matches the aspect ratio of the other attachments and is smaller in each dimension. In our case, the maximum size of the fragment density map image is 1/32 the dimensions of the other attachments, such as the color and the depth. The attachment is an R8G8 image that you can see here, which is mapped to specific areas on other attachments. And this controls the local rendering resolution of each of the areas, with the R value defining the horizontal resolution and the G value defining the vertical. Now, the rendering resolution is proportional to the color values, with 255 indicating the full resolution, 127 indicating half resolution, and so on. Now, the granularity of this on our tile GPU, like in the GL ES implementation, is limited to each tile. So as a result, the tiler then has to choose the appropriate resolution based on which parts of this fragment density map fall into the tile boundaries. The image on the right that you see here shows the tile resolutions that correspond to the fragment density map image on the left. You can see that while the tiles are a lot larger and therefore less granular, the shape and pattern of this foveation matches the fragment density map very well. Now, when I mentioned that these fragment density map images are used as frame buffer attachments, you may have realized that this significantly changes the way FFR needs to be integrated into Vulkan applications. Unlike the iBuffer textures, the runtime has no control over an application's frame buffers. And so as a result, along with the color texture swap chain, we now also have a swap chain of foveation textures in the form of fragment density map images. These correspond to the color image of the same index. When you're using Vulkan, this is automatically created when the color swap chain is created through the VR create texture swap chain call, and will be filled by the runtime with the foveation patterns. Now, this new VR API get texture swap chain buffer foveation call, which for simplicity I'll refer to as get foveation swap chain from now on, is now available to retrieve the foveation textures from the swap chain in the same way that the VR API get texture swap chain buffer Vulkan retrieves the color textures. And so the first two parameters here you see should be identical to the get color swap chain call. And the third one is simply a pointer to receive the return foveation image that's compatible with the same corresponding color image. Now, you may be wondering why this image height and width are being returned with the VK image as well, since the get color swap chain call doesn't provide that. Well, since the fragment density map size is actually determined by the runtime based on the iBuffer size, as well as a few other factors, the app would otherwise have no way of knowing the size of this texture. Now, while this isn't actually needed to attach the fragment density map to the frame buffer and the render passes, it should be used to verify that the aspect ratio and size are compatible with the rest of the images and attachments in the frame buffer. And it could be useful if your app wants to modify the fragment density map. Now, when the application sets the foveation level, using the same VR API foveation level property as GLES, the runtime will then repopulate the foveation images with the new foveation pattern without requiring the app to get any new images. When the foveation level is changed by the app, under the hood, the runtime locks the images and uses the high, medium, and low settings that you might be familiar with to calculate a foveation pattern for that level, which will then be written to the underlying memory for each image in the swap chain. Now, when all of these images are updated, since the VK images do not change, the game will automatically get the updated foveation pattern, as long as it continues to use the same foveation swap chain as before. So now that we have the foveation images, we can get to the fun part. So to enable FFR while rendering, the frame buffer needs to know that it has an extra attachment to use, and that it should use it as a fragment density map to control the tile resolutions. As with all frame buffer attachments, it will first need an image view attachment. This is fairly standard, though with a few specific parameters for the fragment density map that I'll go over shortly. Apart from the frame buffer image attachments, the render pass also needs the attachment description, which again has a few specific parameters for a fragment density map. With that, let's dive into the attachment description. So these four attachment parameters, format, samples, initial, and final layouts, should always be set to the values that you see here. The format is always R8G8, the sample count is 1 since we don't multi-sample this attachment, and the layout should always be fragment density map optimal, since, of course, that's what we're using it for. Now, with that attachment, you'll of course need a standard attachment reference for it, marked here as the fragment density attach ref, which I won't show how to make. But that gets added then to the fragment density map create info extension structure that you see here. And this structure is what gets added as a pnex extension on the render pass create info, just like the multiview extension that you saw earlier. And so with the render pass setup, I'll move on to the frame buffer side of things. Now this is fairly straightforward, since we just need a new image attachment. We simply create the image view for the same R8G8 format and with the color aspect bit, even though it's not really used as a color image. Then the only thing is to make sure that the view type and the layer count still match the color textures, which is important in the multiview case. This is then attached to the frame buffer as an extra image view attachment corresponding to that fragment density map attachment on the render pass. And so you might be wondering, that's actually quite a bit of work on the app side, just to do the same thing that we got by default in GLES. And we're doing all of that for what? Well, just from the implementation, you might have already noticed a few advantages that this has over the GLES implementation. Inherently, this API is more expressive, both for development and for debugging. In GLES foveation, it was difficult to visualize how those parameters map to the tile resolutions, and configuring that foveation pattern became a lengthy process of trial and error. With Vulkan's fragment density map, on the other hand, it's now possible to visualize the control textures directly, removing that guessing from the process. Now we can work with that control textures and know much more precisely how that will map to the resulting foveation pattern when it's rendered. The second one is the ability to have fine-grained control over the foveation pattern and the falloff rate. Even though the foveation pattern on the tiles earlier looked similar to the GLES ones you might have seen before, we have already changed the falloff rates to have better control of the outer tiles. And it extends beyond just that. You could very easily have a triangular foveation pattern, or a rectangular one, or one shaped like an Oculus logo if you really wanted to. Now, another advantage is that this helps pave the way for content-aware patterns to work with FFR. Even though we do pre-populate the textures with a foveation pattern in our runtime, once that goes to the app has full control over that image. If you have a menu, for example, with text at the bottom of the field of view, then you are free to exclude that from the foveation. Likewise, if you have a low contrast skybox covering the top half of the field of view, then you can lower the resolution of that part specifically on top of the foveation pattern that we provide to get some extra performance back. And finally, the fourth advantage is that it can be attached to more than a single render pass. We may be trying our hardest here with the limitations that we saw earlier to keep our mobile renderers single pass for now, but this will allow intermediate render targets, provided that they're compatible with the iBuffer size, to also get the benefits of foveated rendering. Though that's not recommended at the moment, it would be possible to have a foveated multiple render pass renderer. Oh, did you think I was done talking about render passes? Well, fortunately, that's not the case, because we're moving right into Sulkin Subpasses, which is a feature, as Remy mentioned earlier, designed for efficient multi-pass rendering on tiled GPUs. So to start, on a tiled renderer, render passes actually have quite a lot of overhead. This is the diagram that you saw earlier, and this will help you illustrate this. As you see here, the binning and storing actually adds quite a bit of extra computational overhead to the render pass. Now, if we add a second render pass, usually we'll want the contents of the first render pass completed and stored. So unfortunately, we have to go through all of that again. Since you have to store the entirety of both render passes, not to mention you'll probably want to sample the output of some of the textures from the first render pass in the second one, there's a lot of overhead due to that low memory bandwidth. In this two-tile, two-render pass case, we double the amount of stores from 2 to 4. As a result, due to this performance overhead, we end up relying a lot on the single-pass renderers to have acceptable performance on complex VR scenes, which sacrifices some of the graphical effects that a multi-pass renderer enables. And that sounds like a problem. So what if we can take out the extra overhead from binning and storing for the first render pass? Well, that would mean that we need to render all the passes for each tile before storing the completed tile out to system memory. And so these are then known as render passes, subpasses in Vulkan. They allow multiple passes to be rendered on a per tile basis on a single full render pass. The second subpass can then use the output of the first subpass without that output ever leaving the tile memory or the tile cache. And thus, that removes the extra memory bandwidth overhead. In the sample diagram, you can see now that we're back to 2 stores, which, of course, is what we want. However, you do have one significant drawback with subpasses. Since each tile finishes rendering all the subpasses of the subpass before the next one starts, the shaders in a subpass cannot actually access pixels outside of its tile. To prevent sampling outside tile boundaries, the previous subpass output is only available to the next subpass shader at the same pixel location. So this does prevent effects such as blurs from being done with subpasses, but it does enable a whole lot of other effects with minimal performance overhead on tile GPUs. So this might not be necessarily a VR-specific feature, but with how much VR games push the limits of mobile GPUs, this is a great way to improve visuals in ways that might not be possible without it. So one application of subpasses is already actually used in UE4, and that is for occluded translucency. While translucent objects can be naively rendered back to front with a standard depth test in a single pass, there are some situations where that wouldn't work, such as the one shown here, where you can see that the teleportation indicator behind the opaque objects are a different color. This would require that occlusion be determined in the shader, which in a single pass render would not be possible. And normally, this would be rendered in a second pass that uses the depth of the first pass so that it can determine whether or not the pixel is occluded or not. Not only would we need to render a second pass here, but we would actually also need to store the depth, which would be more memory and bandwidth intensive. Instead, each pixel rendered in the second pass only needs the corresponding depth, the same corresponding depth value from the first pass. And so we can actually do the same thing with subpasses here, which works just as well without incurring any of the significant memory or bandwidth overhead. And the translucent objects here get rendered last, but with all the draw calls for translucent objects moved to the second subpass. After rendering the first one, instead of ending the render pass, we switch to the second subpass, where the depth buffer that was used in the first pass gets added as a read-only attachment in the second subpass. There, the translucent shaders can load the value of that attachment, and in this case, use it to calculate occlusion and output a different color if it is occluded. Now, apart from just this one single use case, subpasses would also enable techniques such as more efficient tone mapping or even potentially deferred lighting on tile GPUs. And so we hope that we have provided you some good insight into some of the new features available for you to use in Vulkan for VR, and even some that aren't necessarily exclusive to VR. Now that you can't wait to get started to use Vulkan for your next VR title, we have a few more pieces of good news for you to help get your Vulkan project on its feet. On the Unreal Engine side, every single one of these new features is fully implemented in the engine build on our GitHub as of the 1.39 integrations release. So just build the renderer, select the Vulkan renderer in your project settings, and you're good to go. On the tool side, RenderDoc supports debugging all of the features that we mentioned in this presentation. And the stateless architecture of Vulkan makes this a more stable experience. And also, of course, the standard Vulkan validation layers as well support all the features that we mentioned, which will provide you detailed debugging information when developing, as Remy mentioned, without adding any of the extra overhead to your release builds. If you want to learn more, you can read more about these concepts in detail on our blog post here. So if you have any additional questions on Vulkan renderers or how to use it, feel free to join us in the speaker pavilion, or head over to the developer sandbox afterwards to ask us any of your questions. And thank you.